Hello and welcome to today's webinar, Hardware in the Loop HIL Simulation and Testing with Simulink Real-Time and Speedgoat Target Hardware. My name is Tobias Kuschmieder. I am an application engineer at our MathWorks office near Munich, Germany, focusing on real-time simulation and testing through rapid controls prototyping and hardware in the loop solutions. For this webinar, I am joined by two of my colleagues. Simon Eriksson, who is application engineer that also focuses on real-time simulation and testing from our MathWorks office in Sweden, and Patrick Schenk from Speedgoat, which is responsible for the hardware side of our rapid controls prototyping and hardware in a loop solutions. Before we start, please be aware that this webinar is an advanced webinar which complements a webinar earlier this year with the title Power Electronics and Motor Control Prototyping on CPU and FPGA Target Hardware with Simulink Real-Time. The mentioned webinar deals with all the basics of real-time testing, rapid controls prototyping and Simulink Real-Time. You can find this webinar on our webpage and watch it at any time. In the following presentation, we will build upon this previous webinar and assume that you know the background. This being said, let's start with a technical demonstration before we dive into any slides. At this point, Simon will introduce you to the technology and give you a quick overview of the larger demonstration he will give later.
Thank you, Tobias. Yes, let us dive into the demo parts. System on oil rigs are usually large pieces of equipment, and adding their location, you want to simulate your systems before you deploy them. Here we have a Drawworks system that we have designed, and now we want to verify the manual mode for it before we can go on site and test. The system consists of a PLC controlling the induction motor and a hydraulic brake that powers the mechanical torque to move the traveling blocks for the drilling mechanism up and down. In the manual mode, I will control the speed of the vertical movement through a joystick. So to give you a better view on my setup, the actual hardware, I have here the joystick that gives the speed input in manual mode. I have the PLC itself here. I have the field bus, which is Ethernet IP that connects the PLC with the real-time simulator running Simulink Real-Time. Okay. So let's try to put this back. Okay. So I will now go into Simulink to see how my controller handles this manual mode input from the joystick. So let's open up Simulink. Here I have my model. I will run it. And in the model here you see that I have a scope and a 3D visualization block. So let's open those up. And here in the 3D visualization you actually see the Drawworks and the mechanics of it, and the yellow parts here are the traveling blocks that are moving up and down from the input of my joystick. So I will switch to manual mode through my joystick and release the brake. And now I can move this forward and we will see upwards motion. Okay, so it moves up. We can perhaps zoom a bit better in the time axis here. Something like this maybe. So now the system is running still and we can go down again. And stop. And go down a bit faster perhaps. So yeah, the joystick here provides the speed command to the controller, and here we can see that it follows the movement as I want it. both through the scope and in the 3D visualization. So both the scope and the 3D visualization takes position data that gets streamed up over Ethernet from my real-time simulator into my laptop. So this looks about right, and now we know that the manual mode seems to work okay. Despite nothing from the actual machine is available to us yet, except for the PLC of course. And this is good because it's saving us testing time for when everything else is available, so the mechanics, hydraulics, and the electrical machinery. Okay, so we will look more closely into how we built this simulation later, but for now, back to you, Tobias.
Now that you have a first understanding of the technology we will discuss today, let's have a look at the agenda. First, we will talk in general about hardware-in-the-loop simulation testing, or what is commonly referred to as HIL, and explain how Simulink Real-Time can be used for such a task. To round things off, Patrick from SpeedGoat will complement this introduction with a quick overview of HIL hardware from SpeedGoat. Now that we have an understanding of how software and hardware form one system, Patrick will talk about SpeedGoat and all the available hardware variants which enable you to set up a HIL system that exactly fits your needs. As third part of today's webinar, you will see the hardware and software in action. At this point, Simon will take over and demonstrate how you can use Simulink Real-Time with SpeedGoat hardware with a Rockwell PLC to set up and run an HIL test for an oil drill application. At the end, I will draw a conclusion and discuss next steps to push your projects. To kick things off, let's have a look at a user story from one of our customers. AGCO Fendt is an agricultural equipment manufacturer based in Marktoberdorf, Germany. Over the years, the number and complexity of electronic components in modern tractors has increased drastically. As a result, testing such as for engine and gearbox controller software has become an increasingly difficult task. To accommodate this, AGCO Fendt introduced hardware-in-the-loop benches, including accurate powertrain models and SpeedGoat rack systems, to enable them to implement fully automated repeatable tests. This allows more in-depth early development stage testing and also greatly reduces the need for real vehicles for tests. When using AGCO Fendt's HIL test benches, the engine control unit, short ECU, is connected to a SpeedGoat real-time target machine running models of the tractor hardware, for example drivetrain, sensors and actuators. The real-time target machine provides all the I/O connectivity normally available on the vehicle, for example CAN bus, PWM and analog and digital signals. With hardware-in-the-loop testing begins when the tractor is in the early stages of development. This accelerates the development process, allowing rapid changes to be made based on driver feedback and improving the quality of the software. At last, let me quote Mr. Weinbuch, who is test engineer at AGCO Fendt. He says, SpeedGoat systems offer state-of-the-art performance with application-level support included, enabling detailed modeling of the tractor environment for ECU testing and development. Now that you have seen how our customers use such systems, let's have a look at the different parts that make a HIL test bench. A typical HIL system consists of three different parts. First, the system under test. This usually is an embedded system for production purposes, but it can be any other system containing functionality, for example like a PLC. To test this system and all its functionalities, we need to connect it to the HIL simulator hardware using the available I/Os of the system. The HIL simulator hardware can be seen on the right of this slide. These pictures show what a test rack with different hardware units and a monitor can look like. The simulator hardware itself again consists of different parts. SpeedGoat performance machines that run Simulink Real-Time and the models to test the system on a test. A monitor for direct signal monitoring at the HIL test rack itself, I/O cards to connect the system on a test, power supply for the rack, lots of wiring as you can see on the right, and sometimes, while it is not shown in this particular example, it can also include a test stand with some of the actual sensors, actors and user displays. Now to glue all those different parts together, we are still missing one thing. and that is the software we created in order to test the functionalities of the system under test. The software developed with MATLAB Simulink runs on the SpeedGoat real-time computers using Simulink Real-Time as a real-time kernel. And now that we have seen all the different parts that make a HIL test rack, let's give Patrick a minute to give you a brief introduction to SpeedGoat real-time hardware.
Thank you, Tobias. Later today, we are going to introduce typical application use cases where real-time testing is an integral part of the development process. We will be presenting the available hardware platforms in more detail and introduce the protocol and I/O support typically used in hardware-in-the-loop applications. Hardware-in-the-loop often means very large simulation models and a lot of I/O channels. Matrix and SpeedGoat offer great technology to scale up your HIL solution in regard of simulating application concurrently or integrate thousands of I/O channels, as well as the capability of running certain parts of the model at very high closed-loop sample rates. Last but not least, we will talk about protecting your investments. We assure warranty, long-term availability, and full compatibility of all hardware and software components with latest MATLAB releases. Tobias, it would be great if you can show where the software can be found and how the Simulink real-time workflow looks like.
Thanks a lot for the quick introduction, Patrick. So now it is time to have a closer look at the software for HIL simulations. Referencing the V-diagram, HIL simulations take place on the right side during testing. At this point, the goal is to find the most efficient and safe way to test the deployed algorithm. So obviously, to start with HIL, the controller model needs to be deployed to the chosen embedded platform. You can use Embedded Coder to do this. As you can see on the model level, for HIL simulations, the controller model is being replaced with the corresponding I/O drivers. This represents the communication interface from HIL rack to embedded system. With the controller model deployed to the embedded hardware and the communication interface adapted to the hardware needs, it is time to deploy the rest of the test harness to the HIL system. The model to be deployed consists of the following parts. Please note that this may vary depending on your project. At this point, I want to give you an understanding of the workflow itself. The test vectors that have been used to test the system during the simulation phase, the plant model, the verification methods used to confirm that the system meets the requirements of the project. Now the HIL simulation is up and running. As you can imagine, there are several benefits of a testing approach like this. It is possible to test your algorithm in a safe lab environment with 100% repetition accuracy. By doing that, you can easily automate testing and reuse the test vectors from the simulation. With this approach, functional equivalence from the simulation to the deployed algorithm on the production hardware can be proven. You do not need to spend time and money for complex unit integrations in order to test, e.g. a single change in the code base, or to wait until the test track is ready for use. With a setup like this, you can easily test different and dangerous scenarios without any risk of harming human beings or of destroying costly equipment. Adding to that, you can simulate fault injection scenarios, automate testing without great effort, and calibrate the system. Now that we know which part of the software can be found, I want to take 2 minutes to refresh the workflow knowledge, from simulation to real-time hardware. To deploy a Simulink model as a real-time application, it only takes one push of a button, which automates 3 different steps. We start with a Simulink model on our development computer, where MATLAB Simulink is installed. With automatic C code generation and a supported compiler, a .dlm file which contains the application is being created. This DLM file is then transferred to the target computer provided by SpeedGoat via an Ethernet connection. Once the application is running on the real-time hardware, a very important part is the interaction with the system. There are plenty of different options available. Simulink Real-Time Explorer, which provides target configuration capabilities, flexible parameter tuning and monitoring, design of gauges and displays, and deployment of user interface panels, and many features more. Simulink External Mode, lets you tune parameters from within Simulink from your desktop. SLRT APIs like the C API or the .NET and C# API let you control the real-time application from software projects not building on MATLAB Simulink. MATLAB Guide lets you create a user interface in MATLAB and control the real-time application from within MATLAB. MATLAB command scripts build on the MATLAB API for SLRT and provide an easy way to automate testing. In your project, you're free to use one or more of these tools based on your workflow and interface requirements. That said, it is time to take a closer look at the hardware for such a system using Simulink Real-Time. For this, Patrick from Speedgoat will take over and dive with you in the details of the hardware variants.
Thanks, Tobias. Let's discuss the hardware portion of our solution in more detail. Speedgoat is an associate company of the MATLABworks and provides tailored turnkey hardware solutions. After discussing your project-specific requirements, Speedgoat will provide you with a solution proposal for a ready-to-use configuration, covering your performance and I/O requirements. The delivery typically includes the real-time target machine with I/O modules installed and cables and terminal boards. The Speedgoat driver library extends Simulink Real-Time with the necessary driver blocks required to connect with all physical I/O and protocol interfaces. Cabinets, custom breakout panels, and additional rack mount and wiring services are available as an option. To summarize, Simulink Real-Time and Speedgoat target computer hardware are expressly designed to work together. I'd like to start the introduction by showing some typical application use cases. In aerospace and defense, the hardware under test could be navigation or guidance control units, and extensive scenario testing is required to prove the designs before any live testing. Other examples are the simulation of engines or the test harness for brake control systems. These tests typically involve very complex models with high number of I/O channels, extensive use of communication protocols, or even multiple test computers in order to distribute complexity and scale up the performance. Another important application field is automotive. The simulation of motors and vehicle components is key for early verification of control units. Typical requirements next to analog and digital connectivity are automotive protocols and fast FPGA-based I/O modules for emulation of speed and position signals. Flexible and scalable hardware allows sophisticated testing scenarios and facilitates new technology like ADAS, hybrid, or full electric to be easily integrated into the test environment. We see a growing number of customers in the area of green energy and energy-efficient technologies. A flexible and field-upgradable simulation environment with very fast I/O connectivity and FPGA-based support is key to accurately emulate the real-time components like inverters and electronic devices. Additional important application fields are high-tech industrial automation and machinery and electronics. I'd like to introduce a concrete example on how the performance system is used for the build-up of the hardware-in-the-loop test facility. Gulfstream Aerospace produces high-end civilian business jets and uses two performance machines for jet engine simulation. The Simulink engine models run on the real-time target machines and interface through multiple simulation and measurement I/O points to the aircraft full authority digital engine controller. The performance real-time target machine is the ideal choice for office and lab use. It leverages latest generation Intel Core i7 and Xeon CPUs and optional Xilinx FPGA technology to execute real-time application on multiple cores, target machines, and FPGAs. The Speedgoat platforms are modular, field upgradable, powerful, and cost-effective. The flexible expansion concept allows more than 50 I/O modules to be installed in a single system. The second main platform is the mobile real-time target machine. This system was used as the base for the motor control webinar mentioned earlier today. The mobile system is not just used in the field and for rapid controller prototyping, it as well represents a small HIL system right at your desk, and there is no need for booking time in the lab. This very robust and small system can accommodate up to 12 I/O modules on up to 4 layers. This slide highlights some of the protocol interfaces available from Speedgoat. The flexible expansion concepts of our target machines allow selective integration of required protocols to the system. Speedgoat offers many generic as well as industry-specific protocols. Examples are serial and Ethernet-based or shared memory and time synchronization interfaces. Another important example is the SPI protocol. This protocol is widely used to connect with external devices and specific to hardware-in-the-loop for device emulation. Devices can be sensors, interfaces to embedded control units, or simple AD and DA converters. The task of the hardware-in-the-loop system is to accurately emulate the device with all the protocol-specific parameters. The integration of the protocol specifics with your model in the Simulink environment is straightforward. Versatile driver blocks come with each I/O card and enable seamless integration with your external devices. Furthermore, many industry-specific protocol cards are available. Speedgoat continuously expands the portfolio of supported protocols and has a strong focus on user experience. The usability of the driver blocks is maximized with self-explaining parameters along with documented usage examples. The most important part of the hardware-in-the-loop system is the I/O connectivity. Speedgoat offers a very large portfolio of I/O modules to cover your project-specific requirements. Speedgoat supports emulation of all encoder interfaces typically used in the field. Furthermore, a large portfolio of software programmable passive components enables emulation of various temperature sensors, potentiometers, strain gauges, pressure sensors, and more. Fault insertion cards let you introduce hardware failures in the cable harness. Via software driver blocks, you can shortcut or break physical connections or introduce failure signals in the cable harness. Automated testing of different scenarios is made very easy with the flexible emulation and switching I/O cards from Speedgoat. Hardware-in-the-loop often means large and complex models and a lot of I/O and protocol interfaces. A single performance system in some cases may not be sufficient to adequately simulate all components of the HIL application, so you need to be able to scale up easily. Matrix and Speedgoat offer great scalability options depending on the type of limitation you may reach. Simulink offers a concept called concurrent execution to explicitly introduce tasks to the model. With this concept, algorithmic as well as I/O components are distributed to the available hardware resources to balance the load. Inter-target communication between multiple target machines is available via transparent interfaces like, for example, shared memory. Simulink offers the necessary modeling support with model referencing to adequately describe and simulate the multi-target structure in Simulink. Matrix and Speedgoat development teams have a major focus on further leveraging FPGA-based technology out of Simulink. A fully integrated workflow based on HIL Coder enables flexible integration of FPGAs in your design. These concepts enable closed-loop sample rates beyond 100 kHz and open a full range of new application use cases. It will soon be possible to interconnect multiple FPGA cards within one or multiple systems via multi-gigabit transceivers. We leverage the fast serial Aurora protocol for this purpose. All new Speedgoat FPGA cards by default have onboard multi-gigabit transceiver support, and the performance and mobile target machines have default integration of the necessary physical connections. Matrix as well continuously invests in adding more functionality to HIL Coder. Please contact us if you would like to learn more about the available scalability options. Last but not least, each Speedgoat target machine comes with flexible hardware warranty options. All hardware components are available for a very long time, typically 7+ years. This assures fast extension or replacement of existing systems based on known and working configurations. When you choose the MATLAB Speedgoat real-time testing solution, you can rest assured that the tools will work together and that there will be no version lag or lapses in component support, whether software or hardware-based. MATWorks software development and Speedgoat development teams work closely together to ensure that MATWorks software is fully tested on Speedgoat hardware. You can expect that the most current release of MATLAB and Simulink will be supported on the Speedgoat hardware in the Simulink real-time environment. This concludes my introduction to the Speedgoat hardware offerings. Now I'd like to hand over to Simon for the live demonstration of the oil drill HIL test model.
Thank you, Patrick. As we saw before, this is a simulation of a Drawworks system used in offshore industry, and it allows for component analysis and control logic design. A Drawworks is a mechanism that is the main hoisting machinery that raises and lowers the traveling blocks for the drill. We will use this system model in both desktop simulations and real-time hardware-in-the-loop simulations, where the control logic runs on a Rockwell PLC connected to the real-time simulation of the plant model using Ethernet IP and Simulink Real-Time. Here we can see how my setup looks in reality. Here is the Simulink Real-Time target machine. Here is the PLC, which is the device under test. And here is the Ethernet IP link between them. The target machine is also connected to a display and to my laptop. So let us go into Simulink and look at the actual model. So I'm going to bring up my Simulink model. The system model consists of four main parts: system inputs, a simple verification and visualization part here with scope and the 3D visualization, the control logic part, and the plant model, which are all in this block. I also have a control panel block here. I have a variant subsystem here in the middle containing the controller and the plant model, and this is to be able to switch between desktop simulation and HIL testing quickly. Starting with the plant model, we can see that it consists of two model reference blocks that each refer to a separate model that simulates a particular part of the system. One for the electrical part and one for the mechanical part of the Drawworks. So those you see here. Electrical part, induction machine, and the mechanical hydraulical part of the Drawworks. Here are the control system block. So let's look at the plant models. We are simulating a field-oriented controlled induction machine that is powered through an inverter and a rectifier. What's interesting here is that we are using physical modeling tools like SimPower System or SimHydraulics, and we can combine physical components together with control strategies implemented with normal Simulink blocks and make everything run in real time. For example, if we go into the motion control section here, we have the flux observer and the rectifier controls and the field-oriented induction machine controls for the inverter. And these blocks are implemented with normal Simulink blocks and are combined with these physical modeling tools here. So if we go into the asynchronous machine block, for those of you not familiar with our physical modeling tools like SimPower Systems here, they are physical component-based tools, which means setting up an electrical drivetrain like this can be a matter of configuration using data from the datasheet available on your real motor drive. So here you can set the parameters like pole pairs and the inductions, rotor resistance, and so on, and some more advanced settings. But it's basic configuration data. And the same goes for mechanical and hydraulical systems. So if we look into those, we have the hydraulic brake, which has some hydraulic components in them, and we have the pulleys and the rope and the rope drum, which are mechanical components. So this approach with physical component modeling is a good thing for me, especially since I have a background within mechatronics and not so much within hydraulics specifically. So I can utilize the libraries there quite easily. But if you have the expertise, you can create your own blocks, of course, using the Simscape programming language. Relating this to HIL testing in general, it's good since it gives you a large degree of freedom depending on the different level of fidelity that is needed for your HIL simulations. Okay, so all these different parts will be simulated in real time on the target machine and interfaced with the control logics running on the PLC controller. Now we will see how we can interact with this model and the simulations. So, simulation-driven design, development, and testing of the system. The benefit of this model is that we can reuse it for both desktop design simulations as well as for HIL testing. We have built the model so that it can handle multiple user interactions, or user interactions in multiple ways. You can control it through the Simulink dashboard controls directly in the Simulink model, like we have here. So here we have controls from the dashboard toolbox, and the control system that we have developed has two modes. It has the manual mode and the automatic mode. In manual mode, it provides speed reference for how fast we should go forward or upward or downwards. In automatic mode, we provide the set point for the height. So we give it the height of, let's say, 30, and the control system positions the load at position 30 and holds it there. So the manual mode works like the gas pedal of a car. You give it more or less gas in either upwards direction or downwards direction, whereas the automatic mode, you just set a desired height. A second option for a graphical user interface is the Simulink Real-Time Explorer that comes with Simulink Real-Time, and we will look more into that later on in the demo. I can choose which type of user input that I want in my user input block here. So I have a mask that allows me to easily switch between the three different inputs. So here at the bottom I have test vector. So for more automatic testing, you can have automated test runs using predefined test vectors that you can use to stimulate your simulation to put it into different types of user scenarios or use cases. So if we select that, apply, okay, and then put our system simulation in desktop simulation mode and press play, we will run our simulation and collect the results for comparison with a real-time simulator. So the results will be collected in the Simulink data inspector, and yeah, let's wait for the simulation to run, and so we have some results to look at. Okay, so there are simulation is finished, and we can go into the Simulink Data Inspector to view the results. So here I have my run, I have the signals that I have logged, I can see the hoist height, and look at that signal, and we can look at the motor power and so on. Yeah. So this tool, or the Simulink Data Inspector, will be used then later on to compare two runs against each other. So what happened there when I used the test vectors as an input was that under this mask here in the user input block, I have a signal builder block that has my test vectors, which are data imported from an Excel sheet, and that gets imported into a signal builder block, and that runs the scenario that I want. Now what's left before we go into HIL testing is that we need to implement our controller part. So the control logics need to go onto the PLC. I have chosen to do that through PLC Coder, but I mean, if you would like to implement that by hand, or if you have a legacy control system ready, that's up to you, but you need your controller running on the PLC. So let us go back to a slide that I have and look at what we've done so far. Okay, so the system design and the desktop simulations are now complete. So we have a check on that. And we have implemented our control logics onto the PLC. So check on that. And the last thing that we want to do now, I guess you already know what it is from the slide, is that we want to look at how do we make our plant model run in real time, and so we can do some HIL testing. So next I will show you what we need to do to generate code for our plant model and run it with Simulink Real-Time. The first thing that we need to do is that we need to look at the basic setting of the solver. So let's go back into the model. So here we have our HIL model, or our plant model, that's going to be running on the HIL system. We're going to go into the configuration set. So the solver settings you find up here. To be able to generate code, it needs to be fixed step. You set the fundamental sample time, which is 150 microseconds in this case. And solver settings are important in general, and in our plant model we are using local solvers for the different parts of the physical components. So the electrical parts has one local solver, and the hydraulics mechanical parts has one local solver. You see by the different colors here that they have different sample rates. So this one has the fastest one, 150 microseconds, and this one has a slower one of, I think it's like a 15 milliseconds. So going back to the configuration set again, we can see the other thing that we need to do is that we need to go into code generation and select the system target file. The system target file that we're going to select is Simulink Real-Time. This makes the coder know that, okay, we're going to generate code for Simulink Real-Time. And when we select that, we get a bit more options here. So on basic settings on how to work with the system. So under Simulink Real-Time options, for instance, you can see some things like setting the size of how much data you want to log, and naming the MATLAB object for your real-time application. So let's talk a bit about how we can interface to this model. So on the right and left hand side here you see some blocks that says from host or to host interface. So when I run the top system simulation model in PLC HIL mode, it works as an interface model towards the real-time simulation running on the target machine. We can pass data between a Simulink model and the HIL simulator either through running it in external mode that you find up here, or through these from host or to host blocks that comes with Simulink Real-Time. These blocks let you write parameters and read signals from the target during runtime up into a Simulink model. Since the control logic now is running on the PLC, we need to replace the control logic parts in our model, so the state flow charts basically, with I/O interface blocks from the Simulink Real-Time block library. So if we go in and look here, I will zoom in a bit. Something like that. So here those are the signals come in that we want to send to the controller. And here we get the block that reads out the instructions or the commands from the controller. And that is done through these interface blocks. These blocks are the ones that handle the communication over the Ethernet IP bus. So in general, I/O blocks, as you can call them, work like this. You have a setup block and then some kind of send block or read block. And if you look a bit closer on it for the Ethernet IP here, we have some rather straightforward things. The warm restart parameters, you can set the IP address and so on, and some generic parameters for the field bus Ethernet IP. And then you basically have these send blocks and receive blocks that you attach your Simulink signals to, and they handle sending out or reading those signals from the field bus. When you want to log data from your real-time simulations, you have two main ways. You can log data to your RAM memory of the target machine using normal output blocks like these on the top level of your model. But you can also log to a file when larger amounts of data is going to be collected. Access to the real-time target in the MATLAB workspace makes it easy to write test scripts and to do analysis on your real-time simulations. I have written a simple test script that first runs our test in desktop mode and then configures our model for real-time and reruns the same test on the HIL simulator. So let's look at that script. It works like this. First some simple setups. Then we run our system simulation in desktop simulation and collect the results in the Simulink data inspector. Then we do the same thing, but for the hardware in the loop simulator instead. The nice thing here is that we don't need to rebuild between each test case. We can simply replace the input data file on the target that the simulation reads input data from through this copy file to target function. This saves us a lot of time not needing to rebuild between each run. So let us run this script. This takes a bit of time, and what I want to show you in the meantime is the user interface called Simulink Real-Time Explorer. With Simulink Real-Time Explorer, you can create graphical user interfaces through a drag and drop workflow. Here we see an instrument panel that allows me to control my Drawworks application on the real-time target. Panels like these comes well in hand for creating applications like test benches or operated training systems, because you can export them and run them outside MATLAB and Simulink as a normal Windows application by going to export, and we can export the instrument panel here and let somebody else use it. Now my test script is done, and so let's look at the results. So I'm going to bring up Simulink Data Inspector where I have collected everything. See that here, and here we see my 8 runs. So I have 4 tests that I did run first in desktop mode or in desktop simulation, these 4, and then the same runs but on the hardware in the loop simulator. So here we can easily see that, okay, let's go into run 1 and compare the hoist height signal or the results and the hoist height results from the desktop simulations. And we can see, okay, they differ a bit, and then we can go in and investigate how or why this is. This gives us a nice overview of our runs between desktop and real time. This concludes the demo. I hope you found it interesting. Back to you, Tobias.
Thanks Patrick and Simon for the hardware discussion and the demo. Now to help you for a fast start with the HIL solution, there are different ways to support you. There are on-site trainings which are tailored to your needs and help you getting started as fast as possible. Adding to that, our consulting services can help you throughout the whole project with guidance and support. If there is hardware you need to be supported that isn't, the Speedgoat project-based engineering services might help you to push forward. And then, if you do not want to set up the rack by yourself, just get into contact with Speedgoat. They can help you with custom rack solutions. You need support with the system or the software. You're not sure if it is a hardware or software problem? Just call MATLAB or Speedgoat. We have a unified support structure across both companies, plus an advanced support group at MathWorks to help you solve the problems as fast as possible. As it comes to the conclusion, I want you to remember 3 very important things from this webinar. First, Simulink Real-Time is the only rapid controls prototyping and HIL real-time platform that is 100% integrated into MATLAB Simulink. Second, Simulink Real-Time offers you an easy way to test your application in a real-time environment. And it is the commercial-grade real-time solution from MathWorks and Speedgoat tailored to your project needs. For the next steps, here's the link to the Speedgoat website as well as a link to the MathWorks site. This is always a good place to check on the latest information and products. And please talk to us if you're interested in more focused demonstrations or an evaluation. To end the webinar, here are some links highlighting additional examples. We are recording this presentation, so don't feel you need to hurry up and copying down the links. We will be sending a follow-up email with a link to the recording in about a week or so. You can grab them all then. If you can't wait until then, please don't hesitate to contact us directly through the MathWorks website. We will be glad to assist you. Thanks again for joining us. See you soon.